Welcome to another Midnight Voyage, a space where science becomes story and story becomes serenity. As the world grows quiet and the stars begin to hum above us, you've found your way to a place between waking and sleep. A place where curiosity can drift freely and time moves like a slow tide. Each journey we take here will guide you through the deep past, across the cosmos, and into the inner workings of reality itself. Sometimes we'll wander through the formation of planets. Other times we'll glide along the fabric of space-time, or walk quietly through the footsteps of history. But no matter the destination, the path will always be gentle, mindful, and crafted to help you relax, reflect, and, if you wish, sleep. Before we begin tonight's voyage, I'd love to know something about you. What part of science sparks your imagination the most? Where in the world are you listening from tonight? And just out of curiosity, what time is it where you are right now? Midnight, 3 a.m., or early morning just before the birds sing? Feel free to share your thoughts in the comments and connect with fellow voyagers. This channel is not just a broadcast, it's a community of quiet travelers, each on their own journey. So take a deep breath, settle into your pillow or your chair, let your eyelids soften, and now, let yourself drift. Together, we begin tonight's Midnight Voyage.
Imagine, if you will, a galaxy, billions of stars orbiting in elegant rotation. Now imagine that galaxy wrapped in a vast, invisible cloud, a halo of unseen matter. It is this dark matter halo that holds the galaxy together. Without it, the stars would drift away into the void. They would be lost, but instead, they are anchored by a force that does not glow. This is not just a rare phenomenon. It is universal. Every galaxy, every cluster, every grand structure in the cosmos is shaped and held by dark matter. In computer simulations, when scientists include only visible matter, the universe collapses into clumps. Galaxies don't form properly, the filaments do not stretch across space. But when dark matter is added to the equations, everything comes alive. Galaxies emerge, webs form, structure arises from the chaos. Dark matter is the silent architect. It builds the stage so that stars may perform. But for all we know about what it does, we still do not know what it is. There are theories. Some believe dark matter is made of WIMPs, weakly interacting massive particles. Others think it may be axions, tiny ghost-like particles that drift invisibly through the universe. Still others wonder if dark matter might be something entirely unexpected, a new form of matter, something we have never imagined. We have detectors buried deep underground, shielded from radiation, waiting to hear the faintest tap of a dark matter particle. So far, they have heard nothing, but science is patient, and the cosmos is vast. We may not know what dark matter is, but we know it must be there, because without it, galaxies would fall apart, clusters would dissolve, and we would not be here. Dark matter has no colour, no voice, no warmth, but it is the frame upon which the visible universe hangs. It is the silent force, guiding us, even now. If dark matter is the force that pulls, then dark energy is the force that pushes. It is stranger still, more elusive, and yet more dominant. Roughly 27% of the universe is made of dark matter. Ordinary matter, everything we've ever touched or seen, makes up only 5%. We map dark matter indirectly, through the bending of light, a phenomenon called gravitational lensing. Light from distant galaxies curves as it passes through massive clouds of dark matter. This curvature allows us to see what we cannot see, and when we map the dark matter, we find a vast skeleton of the cosmos. Galaxies aren't scattered randomly. They gather along invisible filaments of dark matter. This is the cosmic web, a massive interlinked structure stretching across the entire universe. Where the filaments meet, we find nodes, dense intersections of dark matter and galaxies. These nodes form superclusters, the largest known structures in the cosmos. Our own galaxy, the Milky Way, lives in one such structure, called the Laniakea supercluster, but the stars are just passengers. The web itself, the highways and intersections, are made of dark matter, invisible, silent, but shaping everything. Like scaffolding, it holds galaxies in place. Like tendrils, it guides the flow of matter and light, and though we cannot touch it, its gravity touches us. Dark matter is everywhere, in the space between galaxies, in the halos that surround clusters, and even gently tugging on your body as you rest now. Not enough to move you, but enough to remind us that we are not alone in the dark. It doesn't shine, it doesn't reflect, it doesn't emit radiation of any kind. Dark matter does not speak in photons, only in gravity. And through that gravity, we have seen its quiet fingerprints. We observe how galaxies bend and twist, how stars cling to their spirals, how light curves as it moves through the cosmos. These are clues, each one a whisper, from something we cannot see. Imagine, if you will, a galaxy, billions of stars orbiting in elegant rotation. Now imagine that galaxy wrapped in a vast, invisible cloud, a halo of unseen matter. It is this dark matter halo that holds the galaxy together. Without it, the stars would drift away into the void. They would be lost. But instead, they are anchored by a force that does not glow. This is not just a rare phenomenon. It is universal. Every galaxy, every cluster, every grand structure in the cosmos is shaped and held by dark matter. In computer simulations, when scientists include only visible matter, the universe collapses into clumps. Galaxies don't form properly. The filaments do not stretch across space. But when dark matter is added to the equations, everything comes alive. Galaxies emerge, webs form, structure arises from the chaos. Dark matter is the silent architect. It builds the stage so that stars may perform. But for all we know about what it does, we still do not know what it is. There are theories. Some believe dark matter is made of WIMPs, weakly interacting massive particles. Others think it may be axions, tiny ghost-like particles that drift invisibly through the universe. Still others wonder if dark matter might be something entirely unexpected, a new form of matter, something we have never imagined. We have detectors buried deep underground, shielded from radiation, waiting to hear the faintest tap of a dark matter particle. So far, they have heard nothing. But science is patient, and the cosmos is vast. We may not know what dark matter is, but we know it must be there. Because without it, galaxies would fall apart, clusters would dissolve, and we would not be here. Dark matter has no colour, no voice, no warmth. But it is the frame upon which the visible universe hangs. It is the silent force, guiding us, even now. If dark matter is the force that pulls, then dark energy is the force that pushes. It is stranger still, more elusive, and yet more dominant. While dark matter makes up about 27% of the universe, dark energy makes up nearly 68%. That means everything else, stars, gas, planets, you and me, all of it, is less than 5%. Dark energy is not a thing in the usual sense. It does not clump. It does not gravitate in the way that matter does. Instead, it is a property of space itself. Not something in space, but something that is space. We first began to suspect its presence in the late 1990s. Two independent teams of astronomers were measuring distant supernovae, exploding stars that could act as cosmic mile markers. By comparing their brightness and redshift, they could calculate how fast the universe was expanding in the past, and compare it to the rate today. Dark matter is one of those laws in motion, not a substance we can touch, not something we can hold in a jar, but a force detectable by its effects. In a spiral galaxy, stars rotate too quickly for gravity alone to keep them bound. If only visible matter were present, the galaxy would fly apart, but it does not. Something unseen holds it together. This unseen mass surrounds galaxies in massive halos, extending far beyond the edge of starlight. These halos provide the missing mass, the explanation for why galaxies stay whole. Dark matter is cold, meaning its particles move slowly compared to the speed of light. This slowness allows it to clump together over time, forming structures on the largest scales. It does not interact with electromagnetic radiation, which means it does not absorb or emit light and cannot be seen directly, but we can map its presence through gravitational lensing. This phenomenon bends the path of light around invisible structures, allowing us to trace the contours of the dark. On the cosmic scale, dark matter forms a scaffold, a framework of filaments that stretch across the universe. Galaxies form at the intersections, falling into the wells created by dense knots of dark matter. Simulations show that without dark matter, the universe would be chaotic and lumpy. Structure would not form. Galaxies would not take shape. Stars would not cluster into spirals or ellipticals. The web would unravel. There are candidates for what dark matter could be. One popular theory involves WIMPs, weakly interacting massive particles. These particles would have mass but rarely collide with ordinary matter, which is why they are so difficult to detect. Another candidate is the axion, a tiny particle theorized to explain certain symmetries in physics. Axions would be extremely light, yet capable of forming large coherent fields. Experiments have been designed to search for both, using deep underground detectors shielded from background radiation and powerful magnets to detect rare interactions. So far, none have been confirmed, but the search continues. Each year brings new data, new limits, new hope. Dark matter is not only important for structure, it also plays a role in the early universe. During the formation of the first atoms, dark matter was already shaping the gravitational landscape, guiding hydrogen into clumps that would eventually ignite as the first stars. It is the hidden hand of the cosmos. Not flashy, not bright, but fundamental. It binds the luminous and the invisible. It is the silent pattern beneath the song of the stars. In the early universe, everything was closer, hotter, denser. Less than a second after the Big Bang, the universe was a sea of energy and particles. Too hot for atoms to form, too chaotic for light to travel freely. But even then, dark matter was already there. It did not interact with the radiation. It did not scatter or glow. It simply responded to gravity. As the universe expanded and cooled, ordinary matter remained tied to light, bouncing and colliding in the radiation bath. But dark matter moved freely, unbound by the electromagnetic forces. It began to cluster, forming the first seeds of structure. These clumps of dark matter grew as space expanded, pulling in ordinary matter with their gravity, shaping the scaffolding on which galaxies would one day form. Eventually, the universe cooled enough for atoms to form. This was the era of recombination. Light decoupled from matter and began its long journey across space. Forming the cosmic microwave background, we can still observe this light today. A faint glow that fills the sky in every direction. It carries with it tiny fluctuations, patterns of temperature and density. These patterns are fingerprints of the early universe, and they match the models that include dark matter. The observed anisotropies in the microwave background, the spacing of galaxy clusters, the rate of large-scale expansion, all of it confirms that dark matter played a crucial role. Without dark matter, the universe would be too smooth, too uniform. Galaxies would not have time to form. Structure would take too long to emerge. The cosmos would look very different, but with dark matter. We see the web, we see the filaments and voids, we see how gravity shaped the universe from the beginning. Even today, the influence of dark matter can be traced back to those early moments. It was not a late arrival, it was there from the first breath of time, guiding matter silently, organizing chaos into complexity, giving birth to form, and as the universe grew, dark matter continued to play its quiet part, unseen but essential, always present, always shaping. It was there from the first breath of time, guiding matter silently, organizing chaos into complexity, giving birth to form, and as the universe expanded, those initial clumps of dark matter became the anchors. They grew denser, drawing in ordinary matter, hydrogen and helium swirling into their depths. This was the beginning of structure formation, the birth of form from formlessness in the densest regions. gravity pulled matter into ever tighter configurations, forming halos, then protogalaxies, then stars. These stars grouped into clusters, and those clusters into galaxies, and galaxies into clusters of galaxies. And always, at the center, was dark matter, invisible but indispensable. The filamentary web that dark matter wove across the universe served as a blueprint, a path for visible matter to follow. The gas flowed into these filaments, cooling and collapsing, creating new generations of stars. As the stars lit up, they began to sculpt the surrounding space. Radiation pushed outward, winds blew, supernovae exploded, and yet the underlying dark matter halo remained, unchanged by light, unmoved by heat, but always shaping. Over billions of years, structures formed at every scale, from small dwarf galaxies to massive superclusters. Simulations show this in breathtaking detail. They begin with random noise, tiny quantum fluctuations, and end with a universe rich in galaxies, walls, voids, and nodes. It is dark matter that allows this to happen. Without it, the gravitational scaffolding would be missing, and matter would spread too thin, never condensing into stars and planets, even today. When we look at the sky, we see only a fraction of what is there. The glowing galaxies, the brilliant stars, they ride upon rivers of dark matter, channels laid down in the earliest moments of time, and our own Milky Way is part of this grand tapestry, born from the same dark flows, shaped by the same silent hand. Our own Milky Way is not alone in the dark. It moves through space, wrapped in its own massive halo of dark matter. This halo is invisible, but it extends far beyond the edge of the visible disk, perhaps 10 times farther than the stars we can see. The stars in the Milky Way orbit at speeds that cannot be explained by the mass we observe. Their paths hold steady even at great distances from the center. This steady rotation is one of the clearest signs that dark matter surrounds our galaxy. Like a vast sphere, the halo provides the gravitational glue. It keeps stars from flying outward. It gives shape to the spiral arms. It protects and stabilizes the galaxy over billions of years. Within this halo are smaller clumps, called subhalos. These may contain dwarf galaxies, or be empty, ghosts of potential, shaped by the same forces that govern larger structures. The Milky Way is part of a larger group of galaxies, called the Local Group, and each member of this group, from Andromeda to the smallest dwarf companions, is also wrapped in dark matter. Andromeda, our closest large neighbour, is also surrounded by a dark matter halo, and in a few billion years, the Milky Way and Andromeda will collide. When they do, their stars will mostly pass by one another, but their dark matter halos will merge, their gravity will entangle, their shapes will distort, and over time, they will settle into a new galaxy. Perhaps elliptical, perhaps something we have yet to imagine. Dark matter will play the leading role in this dance. It will guide the merger, absorb the motion, reshape the outcome. Even now, we are drifting toward this future, our halo brushing against the halo of Andromeda, subtle, silent, steady. We do not feel this, but the motions are real. Tracked by precise measurements of stellar velocities and galactic drift within the Milky Way, we can also study dark matter more locally by observing the motion of stars in the outer halo, by looking at how satellite galaxies orbit, and by searching for microlensing events. We can also search for rare interactions, dark matter particles passing through detectors on Earth, leaving behind tiny hints of their presence. These efforts are ongoing, quiet, patient, devoted to understanding what surrounds us. The Milky Way floats in a sea of the unseen. Its shape, its motion, its past and future are all tied to this invisible halo, and so are we. Now imagine a single particle of dark matter drifting silently through the halo of the Milky Way. It has no charge, no colour, no shimmer. It passes through ordinary matter without a trace. It was born in the earliest fraction of a second after the Big Bang. In a time when the universe was smaller than an atom, it emerged from the chaos, formed not in fire but in stillness, carried forward by the expansion of space itself. This particle does not interact with light. It does not radiate. It does not reflect. It has never been seen, and perhaps never will be, and yet it is real as stars, as real as your own heartbeat for over 13 billion years. This particle has drifted through the cosmos, a quiet witness to everything. It passed through vast clouds of gas. It flowed with the early currents of matter. It helped to draw together hydrogen. It shaped the structure of space. It circled the growing filaments of the cosmic web, not pulled by pressure, not pushed by photons, but always responding to gravity. Eventually, it became part of the growing halo around a young galaxy, what we now call the Milky Way. It orbits still, in a path millions of years long, passing through ancient starlight, through nebulae, through the orbit of Earth itself. Perhaps as you sleep, this very particle has passed through your body, without you feeling a thing. It does not stop. It does not rest. It simply continues. It is one of countless others, each on its own journey, each a stitch in the great fabric of the universe. Together these particles form halos, and halos form galaxies, and galaxies form the web, and the web forms the shape of all things. This single particle, silent and unmeasured, is as important as the grandest star. Because in the cosmos, scale does not determine value, visibility does not define presence, and in this invisible matter, we find the architecture of the visible universe, the frame behind the painting, the breath behind the voice, the mystery within the known. There are many theories about what dark matter really is, each one a lens through which we try to see the unseen. Some scientists believe it is made of particles unlike anything in the standard model. Particles that do not respond to electromagnetic forces, particles that pass through us constantly, but leave no trace except their mass and their pull. One major candidate is the WIMP, weakly interacting massive particle. These were proposed because they fit neatly into extensions of particle physics. They have mass. They interact via the weak nuclear force, and would have been created in the early universe in just the right abundance. WIMPs are elegant. They solve several problems at once, and yet we have never found one, despite decades of searching with deep underground detectors. Despite the careful measurements made by colliders, WIMPs have remained hidden. Another candidate is the axion, a much lighter particle, almost massless, first proposed to solve a different puzzle in quantum chromodynamics. Axions might form a kind of invisible field, a vast ocean of low-energy waves flowing through everything, touching all, but interacting with almost nothing. Some versions of axions could convert into photons in the presence of strong magnetic fields, and so we build experiments in quiet places where the noise of the world cannot drown out the faintest whispers of the cosmos. Then there are the theories that dark matter is not a particle at all, but an echo of a deeper geometry, an extra dimension, a curvature of space that mimics the effect of mass. In these models, what we experience as dark matter is just our perception of gravity spilling in from a hidden realm, a realm just out of reach, curled up at scales we cannot yet probe. Others speculate that dark matter could be primordial black holes, tiny remnants from the first moments of the universe, too small to detect, but numerous enough to provide the mass we observe. Each theory has its appeal, its predictions, its beauty, and yet none have been proven. The universe keeps its secrets close. But the search continues, in labs deep beneath the Earth, in satellites orbiting high above, in the quiet measurement of gravitational waves, in the elegant dance of stars. The question of what dark matter truly is remains one of the greatest mysteries in all of science. It touches not just astrophysics, but particle physics, cosmology, even the foundations of mathematics. It invites us to expand our understanding of what matter can be, to accept that the universe may be more subtle than we ever imagined. Perhaps dark matter is not one thing, but many, a whole dark sector of physics, with its own forces, its own particles, and its own structure, invisible to us not because it hides, but because we have not yet learned how to look. in time, with patience and insight, we may discover the truth. And when we do, the story of the cosmos will be rewritten, not with new stars, but with new understanding. For now, dark matter remains our unseen companion, shaping everything we see, but never showing its face. Dark energy, this cosmic tug of war, will shape everything that is to come, not just for galaxies, not just for stars, but for the very fabric of reality. In the early universe, shortly after the Big Bang, everything was hot and dense, particles collided, light bounced between matter, and gravity pulled the first clumps into being. Dark matter was the sculptor. Its invisible hand guided the flow of matter, drawing gas into filaments, creating the seeds of structure. Every galaxy, every star, every cluster owes its existence to the quiet pull of dark matter. But as the universe expanded, its contents began to spread, the density of matter decreased, the force of gravity weakened, the light from stars scattered further and further, and through it all, another presence grew, dark energy, a strange and persistent pressure, not created by matter, but woven into the fabric of space itself. Unlike dark matter, dark energy did not thin out. As space grew, dark energy filled the new volume, becoming more influential with every passing epoch. Now, billions of years later, dark energy has become the dominant force. It does not cluster or clump. It does not form halos or attract galaxies. Instead, it pushes, gently, constantly, on the large scale of the cosmos. It is a quiet expansion, but its consequences are vast. When scientists measured the brightness of distant supernovae, they expected to find a slowing expansion, a universe gradually decelerating under gravity's pull. But the light told another story. The expansion was speeding up, and it has continued to accelerate ever since. This discovery changed everything. It introduced a new chapter in cosmology, a new force to consider, a new mystery to unravel. We call it dark energy, but we do not know what it is, only what it does. It acts on space itself, increasing the distance between galaxies, stretching the very coordinates of reality. Dark matter and dark energy are like opposite halves of a cosmic balance. One pulls inward, creating complexity, structure, connection. The other pushes outward, creating separation, emptiness, silence. Together, they define the evolution of the universe. Every epoch, every age has been shaped by their dance. In the beginning, dark matter had its moment. Stars were born. Galaxies took shape. Clusters formed along filaments. The universe was loud with light. But now we are in the age of dark energy, an era where the great structures are finished, where the scaffolding has been set, and the distances begin to widen. What comes next depends on how this balance changes. If dark energy remains constant, then galaxies will continue to drift apart. Their light will grow fainter, eventually falling out of view. The night sky will empty, and the cosmic web will unravel. Stars will age and die. New stars will form more slowly, and in time, entire galaxies will go dark. This is the big freeze, an endless cooling, a slow and silent decline into entropy. But if dark energy is dynamic, if it changes with time, then other futures are possible. If it strengthens, the expansion will accelerate more violently. Galaxies will fly apart, clusters will disintegrate. Eventually, even solar systems, even planets, even atoms may be torn asunder. This is the big rip, a dramatic and final unraveling of all structure. If dark energy weakens, the universe could stop expanding. Gravity might regain its grip, drawing everything back inward. Galaxies would collide, the web would collapse, and all matter would converge into a single point. This is the big crunch, a mirror of the beginning, and perhaps the start of something new. A universe born again. We do not yet know which path is ours. The data is not yet complete. The equations remain unsolved. We watch, we listen, We wait. We are suspended between forces we cannot touch. But that shape, every atom, every breath, every moment of time, dark matter holds us close. Dark energy urges us to let go. And somewhere between these two extremes, we live, in the brief balance of a still-forming universe, in the far future, long after the last new star has formed, long after the Milky Way and Andromeda have become one. The universe will have entered a different era. The structures we see today, galaxies, clusters, superclusters, they will remain, but more distant from one another than ever before. Dark energy will continue its work, gently stretching the fabric of space, pushing galaxies beyond the cosmic horizon, until each becomes isolated. An island of stars surrounded by darkness. Eventually, even within these islands, the lights will begin to go out. Stars will burn the last of their fuel, turning into white dwarfs. Neutron stars and black holes. New stars will stop forming. As gas is exhausted and dust becomes thin, only remnants will remain. Cool, diameter, silent, dark matter will still be there, holding the remnants of galaxies together. Its invisible web stretched thin, but intact. It will anchor the ghosts of structure long after the light has gone. But dark energy, always expanding, will widen the space between these remnants. The night sky will no longer show neighboring galaxies. It will be empty, silent, a dome of endless black. Entropy will continue its rise, a law not of choice, but of time. Everything tends toward disorder, toward uniformity, toward stillness. Black holes will slowly evaporate, emitting faint whispers of radiation until they are gone. Atoms themselves may decay, leaving behind only drifting particles and lonely photons. Eventually, if dark energy continues, the universe will be a vast dark sea of cold radiation and ever-expanding emptiness. This is the far future, the heat death, a state of maximum entropy, where no useful energy remains. And nothing more can happen. The arrow of time will still point forward, but there will be no events, no stories, no change. Dark matter, once the builder of galaxies, will remain in form, but without purpose. Dark energy, once the great expander, will have pulled the universe beyond itself, into a silence beyond silence. This is not destruction, but completion, the final settling of cosmic tension. Every star, every planet, every being, every motion will have played its part, and what remains is the memory, encoded in the structure of the cosmos, a faint echo of order within the endless sea of entropy. This is not a tragedy, it is the closing of a symphony, a slow and beautiful fade, where even silence has meaning. Time may lose its shape, without changes to mark it, without boundaries to contain it, but the universe, even then, will carry the memory of its becoming. And perhaps, in some new form, in some quiet rebirth, from quantum fluctuations or the whisper of a multiverse, a new beginning may stir, a new expansion, a new scaffold, a new light. But until then, dark matter holds what little remains. Dark energy carries it all apart. And time continues, not with motion, but with the long patience of the void. Even in that distant future, in the silence beyond stars, there remains one final mystery, one final canvas upon which the universe may write again. The quantum vacuum. To the eye it appears empty, to our instruments it seems still. But quantum mechanics reveals a different truth. Even in absolute darkness, even in a space devoid of matter and light, there is activity, there is fluctuation. Particles blink into and out of existence. Virtual pairs emerge, exist for a breath of time, and vanish again, borrowed from the uncertainty of energy itself. This restless energy, hidden within the vacuum, may seem insignificant, but it holds vast implications. It may have driven inflation in the early universe, an explosive expansion that set the cosmos in motion. It may connect to dark energy, to the force that now drives galaxies apart, and in the far future, when all else has faded, this vacuum energy may remain, a background hum, a flicker beneath stillness. Some physicists propose that the vacuum is not truly stable, that it may be a false vacuum, a temporary state, and if so, it may one day decay, collapsing into a more stable state, releasing unimaginable energy, redefining the laws of physics. If this were to happen, a bubble of true vacuum would form, expanding at nearly the speed of light, erasing the universe as we know it, and replacing it with something entirely different. New particles, new forces, new rules. This is not science fiction, but a possibility rooted in quantum theory. The vacuum is not empty, it is full of potential. In this view, the end of the universe is not simply a fade into silence, but a transformation, a rebirth, a quantum reboot, and beyond even this lie the ideas of multiverses. Realms beyond our observable cosmos, where dark matter may behave differently, where dark energy may be absent, where the constants of physics take on new values. These are not yet proven, but they emerge naturally from our equations, from string theory, from inflationary models, from the very structure of quantum fields. If true, then our universe is but one note in a vast and eternal symphony. And perhaps, just perhaps, dark energy and dark matter, entropy and expansion, are the chords that give this note its shape. In a sea of possibilities, we are a single unfolding, and in the dance of silence and motion, of gravity and energy, the universe tells its story, and we, for a brief time, have the privilege of listening. Let us now imagine the technologies of a future civilization, one that has not only discovered dark matter and dark energy, but learned to use them. These are not dreams born from fantasy, but projections rooted in known physics, guided by equations and constrained by the same laws that govern our stars. First, dark matter reactors, if dark matter is composed of weakly interacting particles. Then a sufficiently advanced detector could evolve into a collector, a chamber designed to trap and concentrate these particles within dense magnetic or gravitational fields. Inside such a reactor, dark matter could be made to interact with ordinary matter in rare collisions, releasing measurable energy. This energy could be harnessed as power, clean, enduring, and sourced from the very scaffolding of the cosmos. Such a reactor would operate in deep space, where the density of dark matter is higher, perhaps near the centers of galaxies, or inside the halos of ancient globular clusters. Then there are propulsion systems. Imagine a spacecraft that travels not by burning fuel, but by riding gravitational gradients shaped by dark matter itself, by modulating local gravitational potential, or using controlled dark matter masses as anchor points. It might move with elegance through the void, guided by curvature rather than combustion. Dark energy poses different challenges. It does not clump, it does not gather, it stretches space. But this very property may one day be used to our advantage. One concept is the manipulation of vacuum energy. If dark energy is a manifestation of the vacuum field, then future technologies might be able to engineer small perturbations in that field, creating bubbles of altered expansion, microenvironments where space itself bends differently. This might allow for warp-like drives, not by moving through space, but by changing the space around the vessel. Other concepts include shielding against the effects of expansion, preserving planetary systems from cosmic acceleration, or creating localized regions of slowed time. And if dark energy connects to a scalar field, a slowly changing energy field that permeates the cosmos, then it may be tuned, like a dial, with the right instruments. We could push or pull against that field, creating thrust without mass, motion without momentum. We might even be able to carve tunnels through space, not wormholes, but regions of space-time defined by energy gradients, mapped and sustained by quantum manipulation. All of these ideas require advances we have not yet made, in materials, in quantum engineering, in the control of gravity itself. But they are not forbidden. They live within the mathematics of general relativity. within the framework of quantum field theory. They are extensions of what we already know, taken to their most elegant and daring conclusions. In this future, energy will no longer be mined, it will be shaped, curved, and called into being. Dark matter will become the clay, dark energy the chisel, and from them, a civilization may emerge, capable of building not just cities or spacecraft, but geometry itself. They will not merely live in the universe, they will sculpt it. Let us now return to the heart of the science, to the very framework of physics, and ask, where do dark matter and dark energy belong? In the grand architecture we have built. To understand reality, physics is a language, a structure of equations, symmetries, and principles that describe how the universe works. At its core, this structure is divided into two great pillars. One, the standard model of particle physics. The other, general relativity. The standard model explains the quantum world, the particles and forces that make up matter. It includes quarks, electrons, neutrinos, and the bosons that carry force. It describes three of the four known fundamental forces: the electromagnetic, the weak nuclear, and the strong nuclear interactions. It is a triumph of modern science, tested to extraordinary precision, yet it does not include gravity, and it does not account for dark matter or dark energy. Dark matter, if it exists as a particle, must lie outside the standard model. Perhaps it is a WIMP, a weakly interacting massive particle, or maybe an axion, a light, ghost-like particle proposed to solve other problems in physics. Neither has been confirmed, but both have theoretical support. We are building detectors, deep underground, shielded from noise, searching for signs of these elusive particles. A flash, a recoil, and a signal that would tell us that something is there. There are other possibilities too, such as sterile neutrinos, particles that do not interact via the weak force and only through gravity. If any of these particles are confirmed, they will force us to extend the standard model, to write a new chapter in our understanding of quantum fields. Dark matter may also emerge from theories of supersymmetry, which suggest that every known particle has a heavier partner, a superpartner. One of these superpartners, the neutralino, has long been a candidate for dark matter, stable, neutral, massive, and hard to detect. So far, experiments at CERN and other colliders have not found it. But the search continues. Then there is dark energy. It is more mysterious still. Unlike dark matter, dark energy is not a particle. It may be a property of space itself. Einstein introduced the cosmological constant, a term in his equations of general relativity that allows for the expansion of space. He originally added it to keep the universe static, then removed it when expansion was discovered. Later, it returned, not to prevent motion, but to explain it. The cosmological constant, if interpreted as vacuum energy, matches the observed acceleration of the universe, but only roughly. Quantum field theory predicts a vacuum energy density that is many orders of magnitude higher than what we observe. This is the cosmological constant problem, a vast mismatch between theory and observation, one of the greatest unsolved puzzles in physics. There are attempts to resolve it by modifying gravity or introducing new scalar fields, like quintessence, a dynamic form of dark energy that evolves over time. Some theories treat dark energy as a sign that general relativity is incomplete, that on large scales. Gravity behaves differently, but the equations of general relativity, like those of quantum field theory, have passed every test, within the limits we can measure. It may be that both theories are right, but neither is complete. What we seek is a unification, a framework that includes quantum mechanics and gravity, that merges the small and the large, the particle and the curve. This is the dream of a theory of everything. In such a theory, dark matter and dark energy would find their proper place, not as mysteries, but as natural expressions of deeper laws. Perhaps they are signs of extra dimensions, or emergent phenomena from deeper fields, or echoes of other universes interacting subtly with our own. We do not yet know, but what we do know is this: dark matter and dark energy do not break the laws of physics. They complete them, they expand them, they demand from us a deeper understanding. They are the dark corners of the cosmic cathedral, waiting for the light of insight. And as we explore them, we remake the very laws that shape our reality. We climb beyond the equations we inherited and write new ones, inspired by what we do not yet understand, but are learning to feel, to understand the true nature of dark matter and dark energy. We must venture further, to the frontier where our best theories meet their limits, to the place where quantum mechanics and gravity must shake hands. This is the realm of quantum gravity. Quantum gravity is not a single theory, it is a quest, a search for the bridge between the very small and the very large. In our current picture of the universe, we have two powerful frameworks. One, quantum mechanics, governs the subatomic world, particles, fields, probabilities, uncertainty. The other, general relativity, describes the curvature of space, the motion of planets, the warping of time by mass and energy. Both are profoundly successful, both are mathematically beautiful, but they are not yet one. When we try to apply quantum mechanics to gravity, to the fabric of space-time itself, the equations fall apart, infinities emerge, and the math breaks down. We need a new framework, a deeper synthesis. This is what quantum gravity seeks. One approach is string theory. In string theory, particles are not point-like, but tiny vibrating strings. Each mode of vibration gives rise to a different particle. The graviton, a hypothetical quantum of gravity, emerges naturally in this framework. String theory also introduces extra dimensions, beyond the familiar three of space and one of time. In some models, dark matter could be particles that exist partly in these hidden dimensions, touching our world only faintly. Another approach is loop quantum gravity. Here, space itself is quantized, built from tiny loops, woven into a granular structure, like atoms of space-time. This discrete nature of space might help explain the behavior of gravity at the smallest scales, and lead to insights about the earliest moments of the universe. In these models, the Big Bang is not a singularity, but a transition, perhaps from a previous universe, or from a timeless quantum state. These ideas have profound implications for dark energy and dark matter. Dark energy, in a quantum gravity framework, may emerge as a residual tension in the geometry of space-time, an energy built into the vacuum, set by the structure of quantum fields, or it may be a sign that space-time itself is emergent, that what we call space and time are not fundamental, but arise from deeper principles: entanglement, information, topology. Dark matter too could be a product of these deeper layers, not a particle, but a manifestation of how matter and geometry interact in a quantum fabric. In such a view, the cosmos is not a container, but a process, a computation, a network, every galaxy, every field, every flicker of light, a node in a vast quantum weave, and in that weave, dark matter holds memory, dark energy sets the rhythm. These ideas remain speculative, but they are grounded in the effort to unify, to make sense of what the universe is telling us. We build particle colliders to explore high energies, we build gravitational wave detectors to feel the tremble of space-time, and we peer into the cosmos, searching for structure, for anomalies, for whispers from the beginning. Quantum gravity is not only a theory, it is a language we are still learning to speak. When we finally master it, we may find that dark matter and dark energy are not separate things, but two expressions of the same principle, two shadows cast by the same deeper light. What that principle is, we do not yet know, but the search continues, and from here, we may turn our gaze toward another horizon, perhaps the beginning of time, or the nature of information in black holes, or even the role of the observer in shaping the cosmos. The story is far from over. To understand where the information might go, we must take a deeper look at one of the most profound ideas to emerge from modern theoretical physics: the holographic principle. This principle was born not from speculation, but from the study of black holes. When researchers examined how black holes behave, they made an extraordinary discovery. The entropy of a black hole, a measure of how much information it can contain, does not scale with its volume as you might expect. It scales with its surface area. The amount of information inside a black hole seems to be proportional to the area of its event horizon, not the space it encloses. This is strange. In everyday experience, more volume means more room for information. More space means more complexity. But black holes suggest otherwise. They suggest that everything that happens inside a region of space could be described by information stored on the boundary of that space, like a hologram. In a hologram, a two-dimensional surface encodes a three-dimensional image, depending on how the light hits it. Depth and form emerge from a flat pattern. The holographic principle takes this analogy to the extreme. It proposes that our entire universe, or at least any region of space-time with gravity, might be fundamentally describable by information on a lower dimensional boundary. This idea is not mere conjecture. It finds concrete realization in a particular framework from string theory, known as the ADS-CFT correspondence. In this model, a universe with gravity existing in a five-dimensional anti-de Sitter space can be fully described by a conformal field theory living on its four-dimensional boundary. The gravitational world and the boundary field theory are mathematically equivalent. Every particle, every motion, every interaction in the higher dimensional space has a counterpart in the lower dimensional theory. This is the holographic duality. It turns our assumptions inside out. Space may not be fundamental, it may be emergent, a projection from a deeper set of rules, encoded not in volume, but on surface. If this is true for anti-de Sitter space, could it be true for our universe as well? We do not live in an anti-de Sitter space, but perhaps some more general form of holographic duality applies. If so, the paradox of black hole information loss may be resolved. All the information that seems to fall into the black hole might still be preserved, encoded on the horizon, and slowly released through Hawking radiation, in a way consistent with quantum mechanics. This view also offers a powerful tool for understanding quantum gravity. Because quantum field theories are better understood than quantum gravity, this duality allows physicists to study gravity indirectly. By studying its holographic counterpart, it opens new paths to explore space-time, entropy, and perhaps even the nature of time itself. The holographic principle also connects to quantum entanglement. Some theorists propose that the geometry of space, the very curves and shapes of space-time, are woven from entanglement, that where there is more entanglement, space is smooth and connected, and where entanglement breaks down, space might tear, disconnect, vanish. This leads to the idea that space-time is not the stage, but the product of quantum information, and so the holographic principle is more than a solution to a paradox. It is a gateway to a new way of thinking, a universe written not in matter and space, but in patterns of information, projected, entangled, and encoded on cosmic boundaries. This idea continues to grow, and from it, new questions arise. What are the limits of holography? Can we test it? Can we find observational evidence? And if the universe is holographic, what is the screen? Where is the boundary? We are only beginning to explore these questions, but they point to a future where the fundamental fabric of reality may be information itself. From black holes to galaxies, from quantum fields to curved space, from entropy to consciousness, it may all be part of a single, interwoven holographic story, still unfolding. Now, let us turn our attention to time. Time, that quiet current we are all carried upon. We never feel it directly, but we feel its passing. We mark it with clocks and calendars, but we know it deeper than that. It is the heartbeat of change, the unfolding of moments. But here's the paradox. The laws of physics, at their most fundamental, do not prefer a direction. They work the same, Whether time moves forward or backward, they are symmetric. And yet, our experience is not. We remember the past. We do not remember the future. We see cups fall and shatter, but never shards leaping up to form a cup again. Heat flows from hot to cold, never the other way around. This is the arrow of time, a one-way path through the dimension we call now, but where does it come from? The most widely accepted answer lies in entropy dash, a measure of disorder, or more precisely, the number of microscopic arrangements that correspond to a macroscopic state. The second law of thermodynamics tells us, in a closed system, entropy tends to increase. This law gives time its direction. But here's the mystery. Why did the universe begin in such a low entropy state? Why did it begin with such remarkable order? That question has haunted physicists and philosophers alike. Now, recall the holographic principle. If the information in a region of space is encoded on its boundary, then the entropy, the disorder, may be deeply tied to that boundary as well. In fact, the entropy of a black hole is proportional to its event horizon's surface area, not its volume. This suggests that the arrow of time might be connected not just to what happens within the universe, but to what is encoded on its edge. Some theorists believe that the growth of entropy in our observable universe could reflect the unfolding of information along a cosmic screen, a boundary we cannot yet see, but which might encode the totality of everything that has ever happened. In this picture, the past, present, and future may all be written in the same field of information, and yet we experience it linearly. Why? Some believe the arrow of time could emerge from the growth of entanglement, the gradual spreading of quantum connections across space. At the beginning, in the low entropy, early universe, there was less entanglement, less connectivity, but over time, as more particles interacted, more entanglement arose, more information became distributed. And as this web of entanglement deepens, so too does the sense of time moving forward. We ourselves are entangled systems, our memories, our identities, our experience of flow may all arise from this spreading wave of quantum linkage. In this view, time is not a fundamental substance. It is not a thread running through the cosmos. It is an emergent property, a reflection of increasing complexity and the deepening of informational structures. The holographic principle invites us to ask, is time merely a projection? A byproduct of decoding a deeper informational script? And if so, what happens at the edges of time? What lies beyond the boundary, where the hologram ends? That question remains open. But as we continue, we may find that time, like space, is not the stage upon which the universe plays out. It may be part of the performance itself. Now, let us turn our attention to time. Time, that quiet current we are all carried upon. We never feel it directly, but we feel its passing. We mark it with clocks and calendars, but we know it deeper than that. It is the heartbeat of change, the unfolding of moments. But here's the paradox. The laws of physics, at their most fundamental, do not prefer a direction. They work the same, whether time moves forward or backward. They are symmetric, and yet our experience is not. We remember the past. We do not remember the future. We see cups fall and shatter, but never shards leaping up to form a cup again. Heat flows from hot to cold, never the other way around. This is the arrow of time, a one-way path through the dimension we call now. But where does it come from? The most widely accepted answer lies in entropy dash, a measure of disorder, or more precisely, the number of microscopic arrangements that correspond to a macroscopic state. The second law of thermodynamics tells us, in a closed system, entropy tends to increase. This law gives time its direction. But here's the mystery. Why did the universe begin in such a low entropy state? Why did it begin with such remarkable order? That question has haunted physicists and philosophers alike. Now, recall the holographic principle. If the information in a region of space is encoded on its boundary, then the entropy, the disorder, may be deeply tied to that boundary as well. In fact, the entropy of a black hole is proportional to its event horizon's surface area, not its volume. This suggests that the arrow of time might be connected not just to what happens within the universe, but to what is encoded on its edge. Some theorists believe that the growth of entropy in our observable universe could reflect the unfolding of information along a cosmic screen, a boundary we cannot yet see, but which might encode the totality of everything that has ever happened. In this picture, the past, present, and future may all be written in the same field of information, and yet we experience it linearly. Why? Some believe the arrow of time could emerge from the growth of entanglement, the gradual spreading of quantum connections across space. At the beginning, in the low entropy early universe, there was less entanglement, less connectivity. But over time, as more particles interacted, more entanglement arose, more information became distributed, and as this web of entanglement deepens, so too does the sense of time moving forward. We ourselves, our entangled systems, our memories, our identities, our experience of flow, may all arise from this spreading wave of quantum linkage. In this view, time is not a fundamental substance. It is not a thread running through the cosmos. It is an emergent property, a reflection of increasing complexity, and the deepening of informational structures. The holographic principle invites us to ask, is time merely a projection, a byproduct of decoding a deeper informational script? And if so, what happens at the edges of time? What lies beyond the boundary, where the hologram ends? That question remains open, but as we continue, we may find that time, like space, is not the stage upon which the universe plays out. It may be part of the performance itself. We must step deeper into the quantum fabric of reality. At the heart of the modern mystery lies a proposal, both simple and staggering. ER equals EPR, a bold equation, two concepts, two ideas, once thought unrelated. Now, perhaps two sides of the same truth. ER stands for Einstein-Rosen, the mathematical model of a wormhole, a bridge between black holes, first described in 1935. EPR stands for Einstein-Podolsky-Rosen, a famous paradox also proposed in 1935 that questioned the completeness of quantum mechanics and introduced the idea of entangled particles. At the time, these were separate curiosities, but decades later, a remarkable idea emerged. What if every pair of entangled particles is connected by a microscopic wormhole? What if entanglement, that strange, non-local connection that lets two particles influence each other across vast distances, is not just a spooky coincidence, but a literal thread woven through the fabric of space-time? In this picture, space-time is not fundamental. It is born from relationships, from correlations, from the invisible web of quantum entanglement. Imagine that everything in the universe, every particle, every field, is part of a vast, entangled whole. Wherever there is strong entanglement, space-time is smooth, coherent, connected. Where there is less entanglement, the fabric thins, space stretches, distances widen, and where entanglement vanishes, space-time may fall apart entirely. This is a radical view. It suggests that geometry, the curves and warps of space and time, emerges from pure information, not from atoms, not from energy, but from entangled quantum bits, what some now call it from qubit. This leads to a new kind of gravity, not imposed upon space, but arising from the structure of entanglement itself. In some models, the curvature of space-time, what we call gravity, can be calculated directly from patterns of entanglement. And if space-time is built from entanglement, then wormholes too are no longer exotic tunnels. They are the geometry of entangled states. Entanglement becomes the thread, and space-time the fabric it weaves. It also hints at something extraordinary. When two black holes become entangled, they may be connected by a wormhole. Their event horizons become the boundary of a shared structure, a tunnel not visible to the eye, but present in the mathematics. even if the wormhole cannot be traversed, it still represents a unity dash, a deeper connection between regions of space and quantum information. This might explain how information escapes a black hole. The radiation that emerges, Hawking radiation, may be entangled with the matter that fell in. The entanglement builds a bridge, a hidden passage, a whisper across the void. Suddenly, the paradox begins to unravel. Information is not lost. It is shared, woven through wormholes, held in entanglement, and released back into the universe. But what does this mean for us? It suggests that the universe is not made of things, but of relations. We are not floating in a container called space. We are embedded in a vast quantum network, a cosmic mind of correlations. Wherever we look, a star, a particle, a black hole, we are seeing not an object in isolation, but a node in the web. And perhaps even consciousness itself is part of this web, entangled not only with matter, but with meaning, if ER truly equals EPR. Then space is not where events happen. Space is the result of events happening. Together. We are, all of us, threads in a quantum loom. And the tapestry we call space-time is still unfolding from the inside out. In the beginning, we imagined the universe as a great machine, a cosmic clockwork, ticking forward, its gears turning according to the laws of Newton. Mass, force, acceleration. The language was mechanical, precise, predictable, but the deeper we looked, the more that image dissolved. What emerged in its place was not a machine, but a conversation, a network of relationships, a system of codes, a dance of uncertainty and possibility. And at the heart of this new vision, we found something unexpected: information, not just as a tool for understanding the universe, but as a foundation of the universe itself. In every equation, in every field, in every curve of space and flicker of light, there is a current of information. Consider the particle. To describe it, we need to know its position, its momentum, its spin, its mass. Each of these is a unit of information, a specification, a digit in the great cosmic ledger. And when we observe the particle, we extract some of that information, but never all of it, not at once. Quantum mechanics tells us there are limits to what we can know. The more precisely we know one property, the less precisely we can know another. This is not a flaw in measurement. It is a feature of reality, a fundamental trade-off, written into the rules of existence. This trade-off is governed by information. Even entropy, which we met as the arrow of time, is an expression of information. It tells us how many possible configurations a system can take, how uncertain we are about its microscopic state. High entropy, many possibilities, little certainty. Low entropy, fewer possibilities, greater order, and so time flows, not because particles move, but because information becomes more distributed, more diffuse, more entangled. Black holes, once thought to erase information, now seem to preserve it in scrambled, encoded form. Radiation from black holes, according to modern theory, may carry away every bit of data, every story, every identity that ever fell past the event horizon. If true, then the laws of physics are telling us something profound. Information cannot be destroyed. It is as sacred as energy, as immutable as charge. It can change forms, hide itself, reveal itself, but never disappear. Even space itself may not be the background, but the product of informational relationships. This is the essence of the holographic principle, that the contents of a volume of space can be fully described by information on its boundary, a two-dimensional screen, projecting a three-dimensional world, and it echoes in ER equals EPR dash, where every quantum entanglement may correspond to a microscopic connection in space-time. Space, time, gravity, not as things that exist on their own, but as manifestations of how information is stored and shared and entangled, which leads us to ask, if the universe is made of information, then what is doing the computing? What medium holds the code? and what rules guide its unfolding. If the universe is not a machine, but a system of information, then physics becomes more than a set of equations. It becomes a language, a grammar for how information moves, changes, and endures. In this view, the laws of physics are not imposed from above. They emerge from the patterns that information must obey. They are constraints, rules of consistency, conditions that make stable structure possible. Start with quantum fields. All particles, electrons, photons, quarks, are excitations in fields that permeate all of space. But these fields, they are not random. They obey strict mathematical symmetries. And symmetry is nothing more than redundancy in information. It's the repetition of patterns across space and time. Wherever symmetry exists, compression becomes possible. Rules become elegant. Laws become universal. And here's the astonishing part. Modern research in quantum gravity suggests that space-time itself may behave like a vast quantum error-correcting code. In digital systems, error correction allows information to survive, even when parts are lost or corrupted. Your photos, your music, your voice in a call, all protected by clever encodings. Now imagine that space is doing the same thing, that the connections between quantum bits or qubits are arranged in such a way that even when some data is disturbed, the whole remains coherent. This is not metaphor. In certain holographic models, the very geometry of space can be described using the structure of an error-correcting code. The shape of space-time, the way it bends and flexes, can be understood as a way to preserve the underlying information from disruption. It suggests a picture in which space is not continuous, but pixelated, each point a node, each link a bit of quantum correlation. As more entanglement is added, space stretches, expands, grows. Gravity itself, that most familiar of forces, may emerge from differences in information density. Where there is more information, space curves more deeply. In this view, Einstein's famous equations are not fundamental but effective. They describe how entanglement behaves on large scales. This brings us to dark energy and dark matter. They have always been mysteries, but perhaps only because we've been asking the wrong questions. What if dark matter is not a particle, but a shadow in the pattern of information, a kind of collective effect, emerging from the way information is distributed and preserved across cosmic scales? And what if dark energy is the result of how entanglement changes? As the universe grows, as regions drift apart, their entanglement decays, and with it, the structure of space-time begins to unravel like a stretched-out net. The acceleration we see, the push into emptiness, may be a side effect of information becoming more thinly connected. In this view, the entire cosmos is like a vast computational process, not running on silicon, but on qubits, entanglements, and geometry. Each moment is the result of the previous one, evolving by rules, not written in stone, but in logic. Physics becomes a story, told by information to itself. Let us return now to entropy. We've spoken of it as the engine behind the arrow of time, as the spread of disorder, the rise of uncertainty. But at its core, entropy is a statement about information. To say a system has high entropy is to say that there are many ways it could be arranged. That would look the same from the outside. It's like seeing a shuffled deck of cards. You know there are countless possible combinations, but little you can say about this one. Without looking deeper, low entropy is order, a special configuration, easily described. High entropy is randomness, many hidden details, more uncertainty. This idea becomes more than abstract when we enter the realm of black holes. You see, black holes have entropy, and not just a little, they have more entropy than any known object of the same mass. Their entropy, as we've discussed, is not proportional to their volume, but to the surface area of their event horizon. This tells us something astonishing. A black hole, the most compact object in the universe, stores its information not in its depth, but on its edge. This dot, dot, dot is a revelation, because it means that information is not erased by a black hole. It is preserved, encoded, somewhere. The radiation that black holes emit, Hawking radiation, is not purely random, not if unitarity holds, not if information cannot be destroyed. Then every bit that escapes carries part of the story, a code, a signature of what once fell in. The laws of physics. They seem to demand this. They do not allow the ledger to be lost. They demand a conservation of information, as strict as conservation of energy, or momentum, or charge. It's as if the universe is keeping track. Every interaction, every decay, every fusion or fission is recorded, not in a notebook, but in the pattern of quantum states that remain. Even when you burn a book, the information isn't gone, it's in the smoke, the ash, the light and heat that scatter into the air. Difficult to reconstruct, but not erased, and so too with the stars that collapse, with the particles that vanish, with the paths that fork and merge and fork again. If this is true, then information is not just part of physics, it is the foundation, the bedrock beneath all processes. The laws we call fundamental may simply be the rules for how information can move, be transformed, but never destroyed. And what does this say about the cosmos? It means that even as the universe expands, even as stars burn out and galaxies drift apart, the information remains, like the faint impressions in clay, left by vanished fingers, like echoes on a canyon wall. Long after the speaker is gone, the story is written. It cannot be unwritten, only rearranged. In this picture, every black hole, every beam of light, every swirling galaxy is a page in an eternal book, not written in ink, but in bits, not stored in paper, but in space-time itself. We do not yet understand the full grammar of this book, but we are learning. One equation at a time, one particle, one photon, one entropy-bound horizon, and in doing so, we come closer to a realization that what we call reality may be nothing more and nothing less than the history of information interacting with itself.
And so, another journey comes to a gentle end. Whether you're still awake or already adrift in dreams, thank you for travelling with me tonight. The universe is vast, full of wonder and sometimes full of silence. But here, in this little corner of the internet, we take our time to listen, to think, to drift. If tonight's voyage brought you peace or helped you learn something new, I invite you to leave a comment or simply a few words about what part stayed with you the most. If you'd like to join me again on future journeys through time, stars, oceans, or atoms, you can subscribe. And if you'd like to gently support the channel, you can do so by visiting the links below. These stories take time, care, and a quiet kind of passion, and your support helps keep this space calm, creative, and ad-free. Until next time, dream slow, sleep deep, and remember, every star you see was once part of your story. Every atom in your body has travelled through time, and every question you carry is a map to the next voyage. I hope you enjoyed our midnight voyage. Until next time, good night.